All right, welcome back. Now we're going to talk about the motion of the particles of gases and how those different motions impact the properties that we can measure and can look at. So we're going to talk about kinetic molecular theory. All right, so kinetic means motion, molecular means molecules, and theory means, well, it's a scientific theory. And so otherwise known as KMT. Kinetic molecular theory of gases is a model to help explain how gases behave when we change temperatures or volume or we do other manipulations to the gases. We can summarize it with the following statements. And these are kind of important things that are really going to help us understand why and how and where and all of that stuff. So first thing is that random motion is one of the most important precepts of kinetic molecular theory. And what it says is that the particles in a gas move in a very, very random, very non-ordered path, and that they are in constant motion. And it is important to make sure that we understand that we know that those particles are moving all over the place. And it's the reason, the motion of the particles is probably part of the reason that we see some of the properties that we do. And so we just need to know that. Okay. We need to also recall or remember that we have negligible particle volume. Negligible volume of particles. Okay. And so what does that mean? Well, relative to the size of the volume of the gas itself, the molecules that make up the gas don't take up a lot of space. And because they don't take up a lot of space, we can almost just throw them out of the equation and not worry about those pieces and parts being there. Yeah, we're going to talk about how that, anyway, moving on. Number 3, the last thing, or the next thing is the interparticle forces are negligible. So the I'm going to go up a little bit here. Interparticle forces are negligible. In other words, the parts don't attract each other in any way, shape, or form. That is one of the fundamental precepts of kinetic molecular theory, is that those particles, they're just bouncing around. They don't do anything. They don't interact. They don't see each other. They smash into each other, and then they bounce right back again. And that is one of the forces, or one of the things that KMT holds as one of its fundamental tenets. So that's one of them. We're going to come back for the next 2 here in just a second. All right, so the last fundamental things that we want to talk about with KMT, okay, so point 4 is that constant average kinetic energy. So we have a constant average kinetic energy. And so what that tells us is that energy is transferred from particle to particle during collisions. But as long as the temperature is held constant, the average kinetic energy of the entire collection of gases is going to be the same, and it doesn't change. The temperature component of kinetic molecular theory is a big part of how we talk about gases and how temperature is related to motion of particles. And so the energy, the average kinetic energy, is a very big determinant in that particle discussion. And then the last point that I want to say here is that average kinetic energy is proportional to the absolute temperature given the molecule of all gases have the same kinetic energy. So at any given temperature, the molecule of gases have the same average kinetic energy. So that's kind of a big deal. And what that does for us then is we can take those fundamental precepts and we can say that KMT helps us to explain those behavior of gases, specifically their pressure and their temperature at a molecular level. We can say that gas pressure is explained by the average kinetic energy of the particles. And so how is that? Well, gas pressure is a result of the average kinetic energy of the particles because we're talking about particles smashing into each other inside a container, but they're also smashing into the walls of their container. And the amount of times that those particles smash into the walls of the container, that's the determining factor for pressure. And so the number of collisions of particles with the wall changes with the change in the average kinetic energy. And so the higher the kinetic energy of those particles, the more collisions those particles are going to have with the sides of the container, the higher the pressure that container is going to develop. If we lower the average kinetic energy of those particles, they're going to have fewer collisions with the walls of the container, and they're going to have a lower pressure as a result of that. Okay. Now, interestingly, when we talk about temperature of a gas, really the temperature of the gas molecules is a measurement of the average kinetic energy of those pieces. And so a gas manifests average kinetic energy as temperature based on motion of particles. So all that can happen inside a gas sample is the particles inside it can respond to that temperature change by either speeding up or slowing down. And so temperature is really just a measurement of how much those particles are moving. The more temperature, the higher the temperature, the more those particles are going to move. The lower the temperature, the fewer those particles are going to move, and they're going to slow down a little bit. And so, in essence, if two gases are at the same temperature, their particles are going to have the same average kinetic energy, according to kinetic molecular theory. And if we double the absolute temperature, or temperature on the Kelvin scale, the average kinetic energy of the particles will double as well. And so that's kind of a cool little factoid that we need to pay attention to. Now, if we're going to talk about this kinetic energy, we have to talk about molecular speed. And we have to talk about this as being an average. And so give me just a second. We're going to erase, move up, and we'll have that conversation continue in a moment. All right. So distributions of molecular speed. So we have discussed that average kinetic energy of particles is dependent on the temperature of the sample, and that's absolutely true. The higher the temperature of a gas, the higher its average kinetic energy is going to be. The lower the temperature of a gas, the lower its average kinetic energy of those particles is going to be. Now, that's an average kinetic energy, okay? And so because it is an average kinetic energy, we could assume, and we should assume, that we're going to have particles that are not traveling at that speed, are traveling slower than that speed, and we're going to have particles that are traveling faster than that speed. And so the graphic that we see here on the right is the Bell distribution of particle speed. And we can see that we have molecular speed is on the bottom, and then the frequency of that molecular speed is on the y-axis. And for the blue curve, we see a taller Bell distribution, or a taller Bell curve, and we would have an average speed, which is going to be the very tall peak right smack in the middle there. Now, if we changed the temperature, we heated it up just a little bit, and we pushed the curve that way, what you're seeing is we get a little bit shorter curve, and we get a little bit fatter and broader Bell curve distribution. And so what it really means is more particles are traveling higher than that average because we pushed the temperature that way. And so that helps us a little bit understand what's going on. Now, we could also imagine that we have particles that are smashing into each other, and we could see that these gas particles could collide, and it's possible to think of and to ponder that sometimes we have very, very elastic collisions where we have two coming in at each other and they both go pinging back that way, or we have one that's kind of moving this way slowly and we have another one coming up faster and it kind of pings and this one goes up and this one goes down. Or it's even possible to imagine where we have some sort of an interaction where one particle is left hardly moving at all and another one zips away at a super, super fast speed. And so really what you have to understand is, yes, this is a statistical curve of the average speed of our molecules or our particles inside a gas sample, but also we're going to have a whole wide range of different speeds of gases and the traveling of those particles inside that sample, because it's an average. That's what has to happen. Whenever there's an average, there has to be something going faster, something going slower. And so that's what we're looking at with that one. Now, in terms of applying kinetic molecular theory to our gas laws. And so if we have an increase in our volume at a constant temperature, well, that's going to cause the pressure to decrease. So if we think about have a container that can expand, okay, our classic piston example where we would have a piston that would get bigger. Now if we took a gas sample and we pulled it up and we allowed that volume to get larger, that's going to allow our pressure to decrease because the number of kinetic molecules that are interacting with the sides of the container is going to be fewer. Because we have fewer kinetic exchanges with the side of the container, the pressure on the container itself is going to decrease because there's going to be fewer unit collisions between the molecule. Okay, so that's changing the volume. If we change the temperature, so let's say we have the same size volume, but we warm the gas molecules up inside it. The kinetic energy of your gas molecules is going to be higher. More of them will be traveling faster. Because more of them will be traveling faster, more of them will smash into the sides of the container that are holding those gas particles, and you're going to see an increase in the pressure from those gas particles as they go up. In reality, kinetic molecular theory is kind of an interesting discussion. It's a great way to think about how the gas particles actually work. There's no math with it, though, which is good or bad, I guess, depending on how you look at it. So that's kinetic molecular theory. We'll talk about it in class again. So.